Good morning, everyone. My name is Andrea Pugnana. I am a PhD student from Scuola Normale Superiore in Pisa, Italy, and I'm going to present a joint work with Salvatore Ruggeri entitled AUC-based Selective Classification. Machine learning and artificial intelligence have become pervasive in supporting decision-making across different domains. As a fact, several tasks can be framed as classification problems. Classifier performance is generally not homogeneous over the feature space, as some instances are more difficult to classify compared to others. This aspect is generally not addressed by how performance is measured. We generally focus on minimizing a risk function R of h, which is the expected value of individual losses over the whole feature space. Therefore, having a low risk on average is what is considered a good performance, despite some cases having been wrongly classified. Overfocusing on average risk can be problematic, especially in socially sensitive contexts, such as credit scoring or healthcare. Let us consider the following example, where we have built an AI system that predicts the illness status of a patient. If we ask this AI system about the patient's status, the model will always provide a prediction regarding the status of the patient, even though it might be uncertain. However, if we think about a human doctor, she might refrain from providing an answer for more difficult cases. For example, she could run more tests for the specific patient, or she can send the patient to another expert. That is exactly the main idea behind selective classification. Namely, we allow classifiers to abstain from more difficult cases rather than always predicting. The general framework is the following. We have a standard classifier H mapping from feature space X to target space Y, and we embed it with a selection function G mapping from X to 0, 1. The selection function determines whether the classifier will predict whenever G is equal to 1 or will abstain whenever G is equal to 0. The pair H and G is what we call a selective classifier. The selection function is built using the so-called confidence function, which maps from the feature space to R. The confidence function should capture the idea of how difficult it is to classify a certain instance. Intuitively, this means that we want to abstain from those cases where the confidence is low. This is generally done by designing the selection strategy as an indicator function of confidence being above a certain threshold theta. We also highlight that there is an inherent trade-off between the classifier performance and the number of instances we reject. We would like to have an increasing performance if we are willing to abstain over more difficult examples. The percentage of instances that are selected by the selective classifier is referred to as the coverage, while the performance measured by the selective risk, which is the expected value over accepted instances of the loss function normalized by the coverage. Therefore, the selective classification problem can be shaped as the minimization of the selective risk under the constraint of coverage being above a certain value C, called the target coverage. There are many approaches to solving the selective classification problem. The main ones are generally model-specific. For instance, the most recent methods for selective classification relied on deep learning, such as SelectiveNet by Kaufman et al., or by using self-adaptive training by Wang et al. Moreover, the general strategy relies on splitting the available data into a training set to train the model and a validation set to calibrate the selection function. The picture depicts how this strategy is generally performed by standard approaches. One of the limitations of current approaches is that they focus mainly on performance measured as an average over individual losses. In imbalanced contexts, a more common measure is the area under the ROC curve, AUC, which measures the ability of a classifier to rank a randomly chosen positive instance higher than a randomly chosen negative one. Therefore, in AUC-based selective classification, we want to maximize the AUC score over the accepted instances subject to a coverage constraint. To give an intuition of how our method works, we consider the following plot, known as a cumulative accuracy profile plot. On the x-axis, we represent in reverse order the ranking induced by the classifier score for the positive class. On the y-axis, we represent the cumulative number of positives. Intuitively, a perfect classifier should assign a score of 1 to all the positive instances and a score of 0 to the negatives. Hence, in the CAP plot, all the positives should be close to the origin. We represent the perfect classifier with the orange line in the graph, while the actual classifier is depicted with a black line. The area under the black curve is a graphical representation of the Gini coefficient, a linear transformation of AUC. In this context, rejecting an instance means removing some area from the graph. For instance, if you remove a positive instance, the area is equal to the gray rectangles. This means we can relate the area after the rejection with the area before the rejection. Therefore, by imposing the inequality between the two areas, we can derive conditions such that the area after rejection is greater than the previous area. More formally, in proposition 3, we bound the score of the classifier such that if we reject instances belonging to such an interval, the AUC is guaranteed to improve. We highlight that the lower bound is obtained when we consider rejecting negative instances, while the upper bound is obtained when rejecting positive instances. We embed this rejection strategy into two different algorithms, plugin AUC and AUC cross. The former exploits the plugin principle and builds a classifier over a training set, but it builds the rejection strategy according to the bounds in proposition 3. These values are estimated over a calibration set. The latter exploits a cross-fitting strategy. Given a training set, we partition it into k-non-overlapping stratified folds. One at a time, we consider the k fold as a validation set, the orange one in the picture, and the remaining folds as a training set, the light blue ones, where we train a base probabilistic classifier h of k. We use the trained classifier to compute scores over the validation set. All these values are then stored together to calibrate the final selection function according to the bounds of proposition 3. Notice that this is an approximation of the unknown population scores of the entire classifier H, since each H of k is built on k-1 stratified folds of the entire training set, which, in turn, is a set of IID realization from distribution D. We evaluated the algorithm over 9 datasets, comparing AU cross and plugin AUC with 4 baselines and considering 3 main metrics. Empirical coverage, which accounts for how close to target coverage we get on a new test set. Empirical selective accuracy, which measures the performance of our classifier. And selective AUC, namely the area under the ROC curve over accepted instances. The measures were computed over 1,000 bootstrapped samples of the test set, and we report in the graph its mean, while the size of data points is proportional to the standard deviation. Regarding baselines, we consider the following competitors. Plugin refers to a model-agnostic strategy, where a base classifier is trained over a training set, which is a subset of available data. We use as a confidence function the maximum between the score of the classifier and 1 minus the score. The selection function equals 1 whenever the confidence is above a certain threshold theta, calibrated over a validation set. S-cross refers to the model-agnostic strategy provided by Pugnana and Ruggeri, where a cross-fitting strategy is considered to build the selection function, without the need of calibrating it over a validation set. As for plugin, we consider the confidence function as the maximum between the score and 1 minus the score. CellNet refers to a deep learning approach provided by Gateman et al. The idea is to build a neural network with a common main body and different final heads. One of these heads is used to predict the score for the actual class, while the other is used to build a confidence function. The network is trained using a loss function which takes into account the target coverage. The final selection function is calibrated on a holdout set. SAT refers to a deep learning approach by Wang et al. The main idea is to add a class to the prediction problem, which stands for abstention. Hence, if the classification problem is binary, SAT will learn to predict 3 classes. The scores for the additional class are used as a confidence function. These are then calibrated over a holdout set to take into account the target coverage and build the selection function. For the sake of space, we report results from adult and give me datasets. We see also that in terms of selective accuracy, S-cross and plugin are the best in terms of selective accuracy. As a fact, the model-agnostic methods exploit the usage of the live GBM classifier, which is a better choice for tabular data. In the adult dataset, we see that the methods optimizing accuracy also obtain good results regarding selective AUC. However, when we consider a mode imbalance scenario, we clearly see a trade-off between selective AUC and selective accuracy, with traditional methods failing to trade off coverage for AUC improvements. Indeed, the only methods succeeding in increasing the AUC are plugin AUC and AU-cross. We envision several directions for future research. First, we will investigate how to extend our approach to multi-class settings, as AUC is especially used in non-binary ones. Second, we will consider the intersection of explainable AI with selective classification to provide intelligible explanations of the reason for abstaining. This could be valuable information, for instance, for informing the human decision maker taking over the decision. Finally, we envision selective classification as a way to avoid uncertain outcomes. Several frameworks deal with uncertainty, such as conformal predictions. Bridging these fields seems an interesting question to address in future works. To conclude, AUC-based selective classification allows a classifier to trade off between AUC improvements and coverage. We provide two new model-agnostic methods that guarantee AUC improvements, testing their impact over 9 datasets. We also envision several next steps for our research. For accessing our implementation, please refer to the GitHub link. Thank you for your attention.